Today, we will learn how to calculate the probability of getting a certain number of defects when a random sample is drawn from a lot. The purpose of a sampling plan is to determine whether or not to accept an incoming lot by checking a random sample drawn from it. The question is, are sampling plans foolproof? Well, obviously not. But by understanding the underlying math, we can improve the quality of decision-making when we apply them. Sampling is based on probability, and we shall see how that works in a real-life case study. We will do it is by looking at different scenarios. Let us say we receive 20 tons of material in 200-liter drums, so we have 100 drums in the consignment. The QA technician samples as per route N plus 1 protocol, which is quite common in the industry. We will assume that the lot is as per AQL, which is defined as 1.5%. Each item of the sample taken is checked for compliance with the spec. The criteria for accepting the batch would be 0 defects in the sample taken. Since it is a go-no decision, the probability calculation will be based on binomial distribution. We will calculate the probability in 3 scenarios. 1. Getting no defects. 2. Exactly 1 defective, and 3. Getting up to 1 defective in the sample. In MS Excel, to find the probability of an exact number of defective items, we use the probability density function of the binomial distribution. For a sample size of 11 drawn from a lot of 1.5% defects, the probability that there will be no defectives in the random sample taken is 84.7%, which is therefore the probability that the batch will get accepted. The likelihood of getting exactly 1 defective, as we see, is significantly lower, at 14.2%. That brings us to the third scenario. When we need to find the probability of getting up to a certain number of defective items in sample, we use the cumulative distribution function. Note the change in formula. The probability of getting up to 1 defective is the sum of probabilities of getting 0 or 1 defect in the sample, which we have just calculated above, and this works out to 98.9%. Let us now try out a couple of numericals using the concepts we have just learned. 1. In a sample size of 25, what is the probability of getting more than or equal to 2 defectives if the lot has 3% defectives? 2. Consider a scenario where the incoming lot has 5% defectives. WSI is higher than the AQL. As per sampling plan, up to 1 defective is acceptable. What is the probability that the batch will get accepted? Let us come to the solutions. For the first problem, probability of greater than or equal to 2 defective items and sample size of 25 for a lot with 3% defects cannot be calculated directly. That is because if we use the cumulative distribution function, considering C equals 2, it will include the possibility of getting up to 2% defects. We need to find for 2 and higher. So instead, we first calculate the probability of getting up to 1 defect. Subtracting that from 100% gives us the probability of getting more than 1 defect, which means 2 or more. This is equal to 17.2%. In the last problem, we are dealing with a batch that does not meet AQL, and hence the probability of acceptance should ideally be low. Let us see. We calculate using lot size of 25, C equals 1, defect rate 5%, and we use the cumulative distribution, and the answer is 64.2%, which is very high. It is like saying 2 out of 3 times, the lot with 5% defects will get accepted as per the sampling plan. We will cover this in the next module where we talk about producer's risk and consumer's risk. Hope this gives you a good overview of how to calculate the probability and of getting a certain number of defects in a sample. We will build upon this in the next videos.